The principle of dimensional homogeneity. In making the remarkable jump from the 5 variables, for example for force, which was a function of L, V, rho, mu, to the 2 variables in the equation of Cf equals to the function of Reynolds. We were exploiting a rule that is almost self-evident axiom in physics. This rule, the principle of dimensional homogeneity, can be a self-evident axiom in physics. This rule, the principle of dimensional homogeneity. Dimensional PDH. Can be stated as if an equation truly expresses in a proper relationship between variables in a physical process, if an equation truly expresses a proper relationship between variables in a physical process, it will be dimensionally homogeneous. That is, each of its additive terms will have the same dimensions. Each of its additive terms will have the same dimensions. This is the main principle in the dimensional homogeneity. All the equations that are derived from the theory of mechanics are of its form. For example, consider the relation that expresses the displacement of a falling body as consider of a falling body has this relation. Each term in this equation is a displacement or length and has dimension L, 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 and L. The left hand side also has the dimension L. The equation is dimensionally homogeneous. Note also that any consistent set of units can be used to calculate the results. Consider Bernoulli equation for incompressible flow. Bernoulli's equation plus gz equals to const. Each term including the constant because the right hand side is constant, no dimension constant, and each term in here also has dimension of velocity. So we should calculate the dimension of the constant here. The term, each term has the dimension of velocity square and also velocity square. So the constant we don't have any information about its dimension can be calculated as a dimension of velocity square also. The equation is dimensionally homogeneous and gives proper result for any consistent set of units. Students count on dimension homogeneity and use it to check themselves when they cannot quite remember an equation during an exam. For example, this is it, the dimension true or false. S example. Or with checking the dimensions, the first dimension is L and the left is L, and in this equation the left side is L and the right side is M2 or S. By checking the dimension, we reject the first form, and backup were faulty memory. We are exploiting the principle of dimension homogeneity, and this chapter simply exploit it further. Variable and constant in the subsection. In this variable and constant. The equation of Bernoulli and the falling body here, and Bernoulli is constant, Also illustrates some other factors that often enter into a dimensional analysis. In these two equations, we have dimensional variables are the quantities that actually vary during a given case. That actually vary during a given case and would be plotted against each other. Against each other to show the data, for example in the Poly-body diagram, S and T are the dimensional variables, and in the Bernoulli equation P, V and Z are variables. Dimensional constant may vary from case to case but are held constant during a given run. From case to case, but are held constant during a given run. During a as it was obvious in the previous relation, the constant shown with the 0 sub and the G also is a constant, so we consider these quantities in a relation as dimensional constant. Pure constant have no dimensions and never did have no dimensions, such as for example a quantity, and never derives from mathematical manipulation. In the both previous relation there are, for example, the constant 1.5, a constant half on the poly body diagram relation, and also the power 2 in the Bernoulli equation is a pure constant. Angles and revolutions. Angles and revolutions are dimensionless. The preferred unit for an angle is the radian. Unit for an angle is the radian. Which make it clear that an angle is a ratio is like when a revolution is 2 pi. And also counting number are dimensionless. For example, if we triple the energy E to 3E, the coefficient 3 is dimensionless. In the, for example, if we triple the energy E to 3, the coefficient 3 is dimensionless. Note that integration and differentiation of an equation may change the dimension, but not the homogeneity of the equation. Integration and differentiation change the dimension, but not the homogeneity. For example, the integration on S dt from the falling body curve S0t the homogeneity is not change but the dimension change to the, for example, LT. And finally, some physical variables are naturally dimensionless, but variables are naturally dimensionless by virtue of their definition. As ratio of dimensional quantities. Quantities such as for example, strain, change in length per unit length, delta L for example, also ratio of transverse strain to the longitudinal strain, and the last one is, for example, the specific gravity. Ratio of density to standard water density, for example. These are physical variables are naturally dimensionless by the virtue of their definition as ratio of dimensional quantities.